We can use all of these pieces of information to calculate the pH of weak acids and weak bases. And so, for example, for acetic acid, CH3COOH right there, you can find the value of the pH if you understand what Ka is all about. So for acetic acid, Ka would be H plus or hydronium, either way is fine, times the conjugate base, which is acetate, and you'll divide by the acetic acid. And if you understand Ka, you can find hydronium, and hydronium will lead you to pH. Now for bases, we'll use the Kb expression, but it's the same idea, which is kind of cool. Now to find out how much hydronium is there, you can use one of those pH meters on the right. And what I want you to see, there was a little video that played initially, but what I want you to see is that as the concentration of the weak acid increases, so we went from 0.0001 to 0.003 to 0.06 to 2 molar, you can see how the pH needle there got more and more acidic as the concentration goes up. So higher concentrations, more acidic, which means lower pH. And we'll see that in this section. So for acetic acid, which I'm going to abbreviate as HOAC, HOAC is a common abbreviation for acetic acid. I'm not totally sure why, to be honest, but anyway, that's how it goes, and I'm just the messenger. Anyway, acetic acid will react with water to make hydronium and the acetate ion. And let's assume that we have a 1 molar solution of acetic acid. That's all we need to calculate the concentrations of the weak acid, the hydronium, the conjugate base, and even the pH. All right, so let's use an ice table to do that. We'll set up the ice table, reactants on the left, products on the right. Don't include water because it's a liquid. When you do that, you can see what the values come from. Now, acetic acid started at 1 mole per liter. That's the only piece in the initial line. Hydronium and acetate are considered to be 0. But you can't have zeros at equilibrium, so hydronium and the conjugate base will both go up by X, while the acetic acid goes down by X. So at equilibrium, we got 1 minus X and X for hydronium and the acetate ion. By the way, that note there, water creates hydronium, creates 10 to the minus 7th moles per liter hydronium at room temperature. And usually that's so small that it doesn't affect the amount of hydronium we're looking at in these problems. Sometimes super precise things will need to take into account the hydronium from water, but we won't have to in this class, so just FYI. The Ka is a number you can look up in the table we talked about. It's also in problem set 3. And for acetic acid, it's 1.8 times 10 to the minus 5. So that equals hydronium times the conjugate base acetate divided by the acetic acid. So that would be X times X for the numerator, or X squared. We'll divide it by the acetic acid, started at 1.00 and went down by X. Now, right now, this is a quadratic formula. You're going to have Ka times 1 minus X equals X squared, and you'll end up with a quadratic formula like we talked about last time. And there's nothing wrong with solving that. If you have the solve button on your calculator, it makes it pretty chill and pretty easy, honestly. However, a lot of times there is a better way to do these problems. So if you have a problem like that, you really should check to see how small X is going to be relative to the initial concentration. Now, X is going to be the amount of hydronium, and the initial concentration for us in this problem is 1.00 moles per liter. So if you can assume that that little minus X is small, you can literally cut it out, all right? Just ignore it, because 1.00 minus the X by sig figs and all that stuff is still going to be 1.00. So if that X is very small, that makes this problem a lot easier, because then Ka, 1.8 times 10 to the minus 5, that equals X squared divided by the concentration of the acid, 1.00, and that's easy to solve, because X then will equal the square root of Ka times Ca, and the square root of Ka times Ca would be square root 1.8 times 10 to the minus 5 times 1 mole per liter. And so that's a lot less math to do than a quadratic, and this is why sometimes people like doing it. The approximate expression, which ignores the 1.00 minus X, it ignores the minus X part, you get Ka equals X squared over Ca, where Ca is the concentration of your acid. When you solve for x, x is literally equal to the square root of Ka times Ca. So as you can see there, we're raising it to the 1/2 power, which is like square rooting. It's 1.8 times 10 to the minus 5 times 1, and the square root of that. So when all is said and done, x comes out to be 4.2 times 10 to the minus 3 moles per liter. And minus log of that number gives you 2.37, which is kind of cool. Now, we don't have to worry about the acetic acid part, because in acetic acid part, it's basically just equal to 1.00 moles per liter, so no problem. On the other hand, this can be a pretty powerful thing. Even if you are a TI expert and you love using the solve button and all that kind of jazz, this can be pretty cool because it just takes less time to enter in your calculator. Now in the lower right there, it says I did this in the calculator. I used the quadratic formula. I got two values of x, 0.0042 and negative 0.0043. And you don't want to use negative numbers in chemistry. It just doesn't work out very well. So in this example, x is 0.0042, which kind of makes sense using our stuff right here. Pretty cool. Hydronium equals square root Ka times Ca if the conditions are right, if x is small enough relative to the concentration of the acid. A way to check this, if 100 times Ka is less than Ca, then you can let hydronium equals square root Ka times Ca. Or if you rewrite this real fast, the pH of a weak acid equals minus log square root Ka times Ca. And that's actually a much nicer way to calculate pH than to go through the ice tables to find hydronium, and then minus log of hydronium equals pH. You can absolutely do that, but it is more work. So if 100 times K is less than C, use it, and pH equals minus log square root Ka times Ca. Try it yourself on some of the problems and let me know how it goes. Here's an example where we have a formic acid solution, and formic acid has a Ka 1.8 times 10 to the minus 4, so a little bit bigger than the Ka for acetic acid in the last problem. And also notice here we're using a really dilute solution. 0.0010 molar is pretty small. And then the last example, we had a very concentrated solution, 1.00 molar. But anyway, we can use this information to calculate the pH of the formic acid solution. If you use the approximate method, hydronium equals square root Ka times Ca. So square root, parentheses, 1.8 times 10 to the minus 4 times 0.0010, that ends up with a value of 4.2 times 10 to the minus 4 and the pH of 3.37. However, if you use the quadratic formula, you get slightly different numbers. Hydronium comes out to be 3.4 times 10 to the minus 4, and your pH is 3.47. So on problems like this, you really need to check if 100 times K is less than C. And 100 times K in this problem is 100 times 1.8 times 10 to the minus 4. That's 1.8 times 10 to the minus 2. And that is not less than Ca, which is 0.0010 or 1.0 times 10 to the minus 3. So in this problem, 100 times K is greater than Ca. And if that happens, you really should use a quadratic formula. And that's what the values are given down below there. So this is just an example of how it doesn't work all the time. But if you check for 100 times K being less than C, it should be good to go.